In this example problem, we're going to look at a pinball machine and how different forms of energy are transferred into the steel ball. So it gives you the mass of the steel ball. It tells you you're loading a spring-loaded plunger, and they give you a spring stiffness, and they tell you a distance that spring is displaced. In part A, they ask for the elastic potential energy when you pull the knob back. So let's look at what's happening here with this spring. So let's say we got this little launcher here, and we got a spring on there. And you probably have some kind of knob and you want to apply a force. Here's the ball that's loaded into that launcher. Now, when you apply a force back, you're doing work. You're applying force over a distance. All right, and as a result, that spring is now going to compress. Right, so we now have the ball and it's been compressed a distance. Right, when you're compressing a spring, that spring displacement is what we call x. In this problem, they tell you that compressing the spring is 0.08 meters. So we're going to stick with meters. So fortunately, it's giving us that. We know that x, which is the spring compression, is 0.08 meters or 8 centimeters. So as a result of you doing work, this applied force, you have changed the energy of that ball. And so at position 1 here, we have the only kind of energy. This ball is not moving, it's not elevated, it's on a spring. It is all in the form of elastic potential energy. And EPE as an equation is equal to 1/2 K times x squared. Again, that's the work that spring could do. It's elastic potential energy. So in part A, they want to know, well, what is the EPE? And we can simply plug in 1/2. K is the spring stiffness constant. K is going to apply 300 newtons for every full meter of pull. Well, this isn't pulling a meter. It's only pulling 0.08 meters. So you're not going to get 300 newtons out of that. But nonetheless, that is our stiffness constant, 300 newtons per meter. And the spring displacement is 0.08 meters, and we're going to square that. So what we end up getting here, when we pull out our calculator, we're going to get 0.5 times 300 times 0.08, and we'll square it. And do that, you get 0.96. The EPE, the answer to part A, is 0.96. And it's energy, right? You got newtons divided by meters times meters squared. That's a newton times a meter, which is what we call a joule. So we have EPE of 0.96 joules. That's our answer to part A. Well, part B says, well, then how much kinetic energy will it have after it leaves the spring-loaded plunger? So let's look at what happens when that spring unloads on the ball. Well, that energy is stored, right? And now that spring decompresses, and this ball now is going to leave the spring. And as a result of work being done, the energy is changing. So it's changing from all EPE to position 2 now. We are all kinetic energy. We haven't been elevated, but the spring has done work and the energy has changed. Well, what kind of work has been done? It's been spring work. What work could the spring do? 0.96. And if it did all of its possible work, well, the energy at position 1 has to equal the energy at position 2 for ignoring outside friction, air resistance. And the energy at position 1 is in the form of all elastic potential energy at position 1. And now it's all kinetic energy at position 2. Well, we just found how much energy we have. We have 0.96 joules of energy at position 1, which means the kinetic energy at 2 has to be the same thing. Right? So our answer for B, we don't have to do any calculation. Because energy is conserved, then the energy the ball has when it's stored as spring energy is now the energy in kinetic energy. Which leads us to part C. How fast is the ball traveling? Well, if that is the kinetic energy, and we know that kinetic energy is equal to 1/2 mv squared, well, now we can plug in 0.96 joules is equal to 1/2. They give us the mass of the ball, right? The mass of the ball is 0.05 kilograms or 50 grams, 0.05 kilograms. I'm just going to put the units in here, and we're trying to solve for v, and we have v squared. Right? Now, keep in mind, if we use meters, kilograms, and seconds as our standard units, a joule is just all those units combined. It's a Newton times a meter, and a Newton is a meter at a kilogram per second squared, right? So as long as all of our units are in joules, if we're in newtons, if we're in meters, and kilograms, and seconds, then we're good to go, right? So we have MKS, that's our MKS system. So I can ignore these units and just solve for it. Well, how do I solve for V? Well, let's multiply both sides by 2. That's going to get rid of the half. Let's also divide by 0.05 on both sides. 0.05. That's going to get rid of that. And then to get the square root out of there, we take the square root of the whole thing. So V is going to be the square root of 2 times 0.96, all divided by 0.05. And that's where our calculator is handy. Second square root. 2 times 0.96 divided by 0.05. And we're going to get that the velocity is 6.196. We'll round that to 6.2 meters per second is our answer for part C. All right, so now we've taken that elastic potential energy. The spring has now done work to the ball. The energy has changed. We're all kinetic energy. So now what happens? Well, this ball is going to go up a ramp. Right? So at the top of the ramp, they tell you something about the height of the ramp. So in part C, you have this ball now has left the spring. It has velocity, and it's going to move up a ramp, right? And we know that the height of the ramp is 0.3 meters from here to here. And this ball is going to be now located here, probably still moving. So if this is position 2, let's call this position 3. It's helpful to label these positions, right? And for part D, they want to know, well, how much energy is in GPE here? So really, D is asking for what is the GPE at position 3? Well, that is going to be equal to the mass times gravity times the height at 3. And assuming the height here is 0, h at 2 is 0 meters, we'll call that 0. Then when you move this forward, the ball is now elevated, right? And when you elevate something, gravity can do work. And so I'm going to plug in the mass, 0.05 kilograms, times 9.8 times the height, 0.3. And that's going to give me the energy in the form of gravitational potential energy. Which means I have, in the form of GPE, I have 0.147 joules of GPE. That is the gravitational potential energy at that point. So that's my answer for D. Well, how fast is the ball traveling to the top of the ramp? Well, now we got to consider that kinetic energy, right? So let's look at the energy at position 3. Energy at 3 is now an object that is elevated. We have GPE at 3. It is moving, or we're assuming it's moving. They want the velocity, so we have kinetic energy at position 3. And is it compressing a spring? Can we add elastic potential energy at 3? Well, the spring is back at position 1 and 2, so there is no spring energy. Right? So this becomes our equation. Now, since energy is conserved, we know that the energy that we started with when I did work to pull the spring, that loaded the spring, is equal to the energy the ball had when the spring finished compressing, and has to be equal to the energy at the top of the ramp. And we found that the energy at the start was 0.96, so this energy has to remain 0.96 joules. So this value is 0.96. And we just found that the GPE at 3 is 0.147 joules. And so now all we have to do is add the kinetic energy. And kinetic energy is 1/2 the mass times the velocity at position 3 squared. And now I'm left solving for V, right? So if I take 0.96 and I'm going to subtract 0.147, I'm going to get 0.813, right? I'm just doing a little bit of algebra. I'm trying to isolate the variable. Mine is 0.147. And I'm going to get 0.813. that is my kinetic energy at position 3. That's what that is right there, just the kinetic energy. And that has to equal 1/2 times the mass, 0.05, times that velocity at 3 squared. And now I'm solving for v once again, right? So I can multiply by 2, just like I did. I can divide by 0.05 on both sides. And I can take the square root, right? The same steps we did before. And now we would have the velocity at 3 is equal to the square root of 2 times my kinetic energy at that point that I found, 0.813, divided by the mass of the ball. So I'll pull up my calculator. I'm going to take that number. I'm going to take the square root of 2 times the answer that I just got, 0.813, divided by 0.05. And I have a new velocity at the top of the ramp of 5.7. The velocity at 3 is 5.7 meters per second at the top of the ramp. Right? So, and that makes sense, right? If I started with 6.2 meters per second and I'm elevated, I'm going to lose some of that kinetic energy as it's converted to GPE. So I'm going to be going slower. That's kind of makes sense. And so I'm going to be going 5.7 at the top of this ramp. All right, so this is a great example problem and where we see this transfer of energy from you doing work on the spring. You got to put energy in there. The ball just sitting on there doesn't have energy. But when you do work by pulling the spring back, you've now stored that work in the form of spring energy, which then can do work on the ball, give it kinetic energy. And then as the ball goes up the ramp, gravity's doing negative work. It's actually removing the kinetic energy and converting it into gravitational potential energy. So it's slowing down and storing that energy in the form of GPE, which you'd imagine that ball could roll back down, right? And it would speed back up and have more KE. So again, 3 types of energy. Energy is always conserved, assuming you ignore friction and air resistance, and we can set all of those energies equal to each other to find the missing pieces.